Hi, everyone, and welcome to the YouTube channel, An American Professor. We're going to continue the lecture series on the basics of reinforcement learning, this time talking about controls in reinforcement learning. Last time, I discussed a lot of details about state in reinforcement learning. So let's continue our read along. Be reading this article that I wrote called What Kinds of Controls Are Possible in Reinforcement Learning Problems? First, let's ask, what is a reinforcement learning problem and why are controls important for them? Reinforcement learning is a problem where an agent tries to learn how to maximize its reward by interacting with its environment. Decisions, otherwise known as controls, are important for reinforcement learning problems because they help agents learn which control in a given state is associated with the greatest rewards. There are many different reinforcement learning algorithms that help discover what are the best controls, those controls that lead to the greatest rewards. In future tutorials, I will cover these algorithms in greater depth. I'll only talk about some of the more well-known ones today. Different reinforcement learning control algorithms can be combined to overcome some of their individual weaknesses. For example, reinforcement learning algorithms could encourage exploration early on during an agent's training in order to avoid getting stuck in local optima or finding suboptimal policies for the agents. In addition, reinforcement learning control algorithms can be used to help an agent recover from mistakes and return to the task at hand. Properly tuning reinforcement learning control selection is an important part of solving reinforcement learning problems. After an agent has been trained sufficiently, it would then switch to exploiting its knowledge, the knowledge it's learned from early on, to obtain the greatest possible sum of rewards into the future from any given state during the implementation or testing phase. For more on state, see my previous post right here that I discussed in the last video. The set of all possible controls is referred to the control space, similar to how the set of all states is the state space. This space for controls in most model problems is finite, especially for games. You move the piece here, you move the piece there, etc. However, the control space can easily be infinite in problems where continuous controls are required. Think about a system that's stochastic and you make a control decision according to some probability. Probabilities are continuous in nature and hence infinite. In reinforcement learning, the state control space is often too large, so the set of all possible state control pairs or tuples is often too large for an agent to search through exhaustively. So it must use some form of approximation in order to focus its search. There are two main types of reinforcement learning algorithms, value-based and policy-based. Value-based methods aim to directly estimate the value function, which gives the expected return for taking a given control in a given state. Policy-based methods aim to directly learn a policy, which is a mapping from the state space to the control space. So you give a policy some state, it'll output some control. Usually it's deterministic, but it could be stochastic. So in one state, you have some probability of outputting some control. But right now, let's just think of deterministic mappings. Also, like I said, they could either be deterministic or stochastic. Both types of reinforcement learning algorithms have their advantages and disadvantages, and there is significant ongoing research into developing new and improved reinforcement learning control algorithms. Now let's discuss some of the common reinforcement learning control algorithms. RL algorithms can be used to solve a variety of different types of control problems. Some of the most common RL control algorithms include Q-learning, SARSA, Monte Carlo methods. For Q-learning, This algorithm is used to find the optimal policy for an agent in a Markov decision process, an MDP. Q-learning can be a model-free or a model-based reinforcement learning algorithm. When I say model-free, I'm just meaning it's learning from samples, but it doesn't have a model of the agent's dynamics. If it's model-based, that's assuming there's a model of how the state is being updated according to the influence of the control. If you have a model, great, use it. If not, you're going to use a model-free approach. For SARSA, this is actually, it's a misconception in the literature that this is its own thing. It's actually can be made to fit the TD learning framework. So SARSA is very similar to TD learning, and it's actually could be thought of as a special case of TD learning. But for Monte Carlo methods are interesting. These are RL algorithms that can be used to solve both MDPs and partially observable MDPs called POMDPs. And I'll be talking about these more in the future because this is what kinds of models I use in my own research, and I have extensive experience with them. Monte Carlo methods are typically either on policy or off policy. On policy reinforcement learning algorithms learn from experience sampled from the current policy, while off policy reinforcement learning algorithms can learn from experience sampled from any arbitrary policy, even if that policy is not the optimal policy. Each of these RL algorithms has its own strengths and weaknesses. So it is important to choose the right algorithm for the specific problem that you are trying to solve. Next, let's ask, how do I choose the right type of control algorithm for your RL problem? There are many different types of RL control algorithms. I've named several. And the choice of which one to use depends on the specific optimization problem that needs to be solved. For example, if the goal is to find the optimal path through a maze, then an algorithm such as tabular Q-learning, where all the state control pairs can be fit into a table, that would be well suited for that kind of problem, as it can be broken down into a finite set of states and a finite set of controls. The states could be taken as the maze positions, and the controls could be the normal map directions: move up, down, left, or right, or stay put. However, if the goal is to move a robotic arm to move objects around in a workspace or a task space, then a different kind of RL control algorithm is needed, one that is capable of working with continuous spaces and continuous controls. The choice of RL control algorithm is an important one, and it is important to select the right algorithm for the specific optimization problem that needs to be solved. Some RL problems are more suited to tabular methods, while others are more suited to function approximation methods, such as using neural networks for control. Those are also known as deep Q networks or DQNs, and I'll be talking about these in the future, showing implementations of them and applying them to real problems. The second thing to consider when selecting an RL control algorithm for your problem is the size of the state space and control space. Tabular methods are only feasible for small state spaces, while function approximation methods such as DQNs can be used for larger state spaces or more complex state spaces. The third thing to consider is the nature of the reward function. Some RL problems have sparse rewards, while others have dense rewards or more frequent. An example of sparse rewards is when an agent is only rewarded for winning a game that carries on for many stages of decision making, and for every other stage it receives a 0 reward signal, which is uninformative. Imagine an agent going through a maze and it only receives a reward if it makes it out the other side. If it doesn't get any reward at other points throughout the maze, it would be hard for it to know or realize it. Is it making any progress? Finally, you should consider the computational resources available to you. Some reinforcement learning algorithms are more computationally intensive than others. If you have limited resources, you may need to use a less computationally intensive algorithm. For example, in my own research, I've been training some very complex DQNs recently, and they take a very long time to train on my personal computer. So I'm starting to migrate some of that neural network code to run on Google's Colab tool. This is one option for speeding up complex RL algorithms that are computationally intensive, that is to get access to more GPUs. Google's Colab tool is a very nice and free resource for deep learning engineers and hence deep RL engineers. Also, the slower code I was using before was based on Keras, but after updating my DQN code to run using PyTorch, it's orders of magnitude faster. And I'm not exactly sure why. The PyTorch DQN code is just much faster. It went from hours of training to mere minutes, which is wonderful for speeding up development time of my research. 4, let's go through some examples of how different controls can be used in real-world reinforcement learning problems. Reinforcement learning controls can be used in a variety of real-world problems. For example, consider a robotic arm that needs to be trained to reach for a specific object. In this case, RL can be used to tune the arm's control parameters so that it reaches the target with the highest probability. In robotic controls, RL is used to optimize the control inputs of a robot so that it achieves some goal. For example, a robot might be programmed to wander around a room and collect all the objects in the room. The RL algorithm would learn the best way to control the robot's motors so that it can collect all the objects as quickly as possible. In game playing, RL is used to train an artificial intelligence and AI to play a game such as chess or Go. Here, the control would be where to place what game piece, adhering to the rules of the game. The AI agent is programmed with a RL algorithm, which allows it to learn from its mistakes and gradually get better at playing the game. Eventually, the AI agent will be able to beat human opponents at the game. Another example of RL controls in action is autonomous driving. Here, RL can be used to optimize the control system so that the car drives safely and efficiently. Additionally, for autonomous driving, the car could also learn the best way to navigate through traffic based on information such as the current traffic conditions and the destination, while maybe additionally getting the user there on time to meet some deadline. In an agricultural setting, RL could be used to control irrigation systems, how much water to use, how much fertilizer to use, etc. The system would learn the optimal amount of water to provide to plants based on factors such as weather conditions and the type of plant. Other applications of RL in a gardening setting could be where to place the seeds and at what depth to plant those seeds. In a factory setting, RL could be used to control assembly line robots. The system would learn the most efficient way to assemble products based on data such as the number of products to be assembled and the order in which they need to be assembled and the rate at which they should be assembled. RL is a powerful tool that can be used in a variety of different settings, including industrial settings. In the medical space, RL can be used to control robotic processes. In this application, RL can be used to adjust the control parameters of the prosthesis so that it functions optimally for the user. Thus, RL controls can have a wide range of real-world applications. And I want you to dream big. Think about how RL can be applied to your own unique problem. I want I want to spur that creativity in you to see how you could apply RL to your own problem or problems. I am most excited about this for future research, as it seems to be the least explored of the fields that I've seen in the medical space, but one of the most useful for helping humanity in myriad ways. The agricultural setting is also really interesting to me. In neural network training, RL is used to optimize the weights and biases of a neural network so that it performs well on some task. For example, a reinforcement learning algorithm might be used to train a neural network to recognize handwritten digits with high accuracy, as in the case of MNIST dataset. And this is where we need to separate prediction from control. For prediction, a deep neural network is used. And that's more for the MNIST data set. So it's not really a control kind of data set. But when you combine neural networks with control, you get DQNs. And that's where the real function approximation comes into play for reinforcement learning. In conclusion, RL controls can be used in a variety of ways to optimize performance or solve specific control problems for very challenging problems, where the best strategy for control is probably not known currently. For instance, they can be used to calculate the optimal control inputs for any system given a set of constraints and objectives, or to find the best way to control a possibly nonlinear system. As such, RL control algorithms represent a powerful tool that can be used in many different ways to improve the performance of highly complex systems that are nonlinear, noisy, or continuous. Until next time, consider becoming a Medium member to never miss one of my stories as I publish them, and gain unlimited access to my writing and the writing of other authors by following this link right here. That's it for this video. Don't forget to hit that like and subscribe button.